Hey, we're starting our next unit here. This is unit 4 for us, and it's all about work and energy. So let's get on it. So here's the thing: energy is probably the most important concept in all of science. Basically, everything that exists is just a different manifestation of one thing energy. Like literally, everything in the universe is just energy. You Sound, light, motion, even matter itself, E equals mc squared. Everything you can think of, thoughts themselves are just manifestations of energy. So we can't really say what energy is, but we certainly understand how it behaves. And that's what this unit is going to be all about. So we've got to start off with how we're going to measure this stuff. So we're going to measure in units called joules. Now, joules refer to any kind of energy. So it could be electricity, it could be heat, it could be light, it could be motion, whatever. We're going to measure in units called joules. And one way of defining joule is say 1 joule is the amount of energy that an object gains when you apply 1 Newton of force to it and your hand moves the distance of 1 meter. So if 1 Newton of force acts across 1 meter of distance, the object gains one or loses 1 joule of energy. So let's just take a look at this here. I've got an object that starts off here. Pretty cool, huh? I like that I did that. Okay. I apply 3 Newtons of force to it, and I push those 3 Newtons across a distance of 2 meters. Well, guess what? The object is going to go faster. It's going to gain energy. We're going to say in a minute that's called kinetic energy, but right now we're just going to call it energy. So I put 3 Newtons of force across a distance of 2. That's 6 joules. So the object just gained 6 joules of energy as a result of that push I gave it. Now, energy is a scalar quantity. It doesn't have a directional component. If I'd push this the opposite way, I wouldn't say it now has negative 6 joules of energy. It just has 6 joules of energy of motion, what we're going to call kinetic energy. Now, I can I can take away energy. I can do negative 6 joules of work, if you will, and take away 6 joules. But the negative or positive descriptor does not apply to a direction, just whether it's gaining or losing in this case. So let's just go ahead and be specific about this concept: kinetic energy. Kinetic energy is energy of motion and is defined by an equation that should look pretty familiar to you. It looks just like the one I say is one of the most important, useful equations in all of physics. K equals 1 half mv squared. Kinetic energy, which we're just going to use the capital letter K to represent, is equal to 1 half the mass of an object times the square of its velocity. It's just like delta x equals 1 half at squared. Same basic form of equation, right? So basically, when an object gains speed, if this goes up, then this goes up by the square of this. Okay, so kinetic energy is just energy an object has by virtue of moving. Now, kinetic energy, if you look at this, is definitely proportional to the square of velocity. So what that means then is if an object goes from having velocity v to velocity 2v, well, 2 squared, it would now have 4 times as much kinetic energy. On the other hand, the kinetic energy is just directly proportional to mass alone. So in this case, if I took an object traveling at v and doubled its mass and still had it traveling at v, it would have twice as much kinetic energy. Now, work is a really important concept that we're going to work with quite a bit this unit. So work is basically defined as the change in the energy of an object, or later on we'll say a system of objects. And work is done anytime a force acts on an object and moves that, is applied to that across a certain distance. So if I push on a wall with 100 newtons of force and the wall doesn't move, I didn't transfer any energy to the wall, so I'd say I didn't do any work on the wall. I didn't give it or take away any of its energy. On the other hand, if it moves the distance, then I have done work. I have changed the energy of that object. So work is basically energy transfer. So I'm going to measure it in joules. Force is going to be measured in newtons, but it's important that I measure distance in meters because the definition of a joule is such that it requires that the distance measurement be done in meters, not centimeters. So when we're doing labs, you got to remember to convert centimeters to meters if we're going to calculate the work done in joules. All right, so this is not really the most useful idea that we're going to encounter in this unit, but it is kind of useful for today's lesson. It's called the work energy theorem. And the work energy theorem basically says this: the sum of the work done on an object is equal to the change in its kinetic energy. In other words, if you take an object and the sum of the work done on it leads to a positive uh, work, then I'm going to have a positive change in its kinetic energy. It's going to gain energy. And if the sum of this ends up being negative work, then it's going to lose energy. If the sum of this is zero, then I didn't change its kinetic energy. It's going to go at the same speed. Let's take a look at this. All right, again, energy is scalar, but still we do have a direction associated with the force, right? Force is a vector. So it turns out that the direction at which I apply a force relative to the velocity vector, remember force, the direction of acceleration is always the same as the direction of the force applied. All right, so here we go. So if a force acts in the direction of motion, an object's moving this way and I push this way, it is going to do positive work and the kinetic energy is going to go up. All right, so it increases the kinetic energy. So the object here has 100 joules of kinetic energy because it's in motion. I apply a force of 10 Newton across a distance of 4 meters. Well, the work done would be 10 times 4, that's 40 joules worth of positive work that was done because the work was directed in the same direction as motion. It's going to cause it to increase its kinetic energy. So it starts off with 100 joules, it's going to end up with 140 joules. It's going faster because I did positive work. But what if I push it the other way? So I'm going to do the same thing. Now I have this object. It has 100 joules of kinetic energy, just like I did before. But this time, the force I'm applying to it, same amount, same magnitude, 10 joules, 10 newtons, but I'm pushing the other way. It's trying to go this way, and I'm pushing it the other way. Well, I'm going to cause it to slow down. Duh, right? So I would say, in this case, I have a force of negative 10 newtons because it's going opposite the direction of the object's motion times the distance of 4 meters does negative 40 joules worth of work. Since the force is being applied opposite the direction of motion, it's clearly going to cause it to slow down and lose kinetic energy. So it goes from having 100 joules, I did 40 joules worth of negative work. So I'm going to take away 40 joules. It now has 60 joules. And from that, I could calculate using the equation what, if I know its mass at least, what its speed is. Now, of course, everything we've done before, we're going to do again. So if a force acts at an angle to motion, it's only the component of the force that's acting in either in or against the direction of motion that's going to do work on the object, right? So in this case, the vertical component isn't really causing it to gain or lose motion. It's just that forward component here. So in this case, it would be F cosine theta times the distance that that force is applied that's going to cause it to have work done on it. That's going to do either positive, in this case, positive work on it since it's moving to the right and this is moving to the right. All right. Well, let's just work through one here, okay? So let's see what I've got here. I've got a 10 kilogram mass. It's traveling to the right at 10 meters per second. I'm applying a 100 Newton tension force at 60 degrees, but it's directed in such that the horizontal component of this tension force is acting against the direction of the object. So it's going to do negative work. So it's only the horizontal component. So 100 times the cosine of 60 uh, times 3 meters, because we're going to say we're going to apply this as this moves 3 meters. This is going to apply. So basically, 100 times the cosine of 60 is 50 newtons times a distance of 3 meters. I do 150 joules of negative work. I'm going to take 150 joules of energy out of the system. All right. So let's just see how fast it's going to go. So I had 10 kilograms that was traveling at 10 meters per second. So 10 squared is 100, and half of 10 is 5. So that means I had 500 joules to start with. I did 150 joules of negative work. So I took 150 away from it. So now it's only got 350 joules. So now I can figure out how fast it's going. It has 350 joules of kinetic energy. I put that here for K equals 1 half m. It's still a 10 kilogram object. And I solve for V. I solve for V, and I come up with 8.3 meters per second. Look, I had a component of this force acting in a direction against this motion, and so it lost kinetic energy. It went from having a velocity of 10 meters per second to a velocity of 8.37. Now, it's important to note, though, if the force is directed perpendicular to the object's motion, I'm not causing it to gain any speed. I'm not causing it to lose any speed. So this force actually does not change the kinetic energy of the system. It does no work on the system. So a force that's perpendicular motion does not change the kinetic energy of a system and therefore does no work. Now, this may seem kind of, so what? Until you consider this. Orbiting objects are a big deal in physics. All right, we're gonna study that later in the year. But basically, if this is, say, the Earth and this is the moon has a velocity going perpendicular to its orbital path, and gravitation is pulling the moon straight towards the center of the Earth. So if you think about it, at any moment in time, the moon's velocity is one way, and the pull of Earth's gravity is perpendicular to that. So although the pull of Earth's gravity is going to cause the moon to change direction, it's not going to cause the moon to go any faster or slower because the gravitational force is always going to be perpendicular to the moon's motion. And think about it, the moon isn't going faster and faster and faster or slower and slower and slower. It's always going the same speed because the force of gravity acting on it is always perpendicular to its motion and therefore does not work. All right, let's look at a tricky one here. Oh man, these ones can freak you out unless you just come to terms with the idea of what work is and keep in mind the motion of the object. So let's see what I've got here. I've got a 6 kilogram object uh, that is falling downwards. That's Mr. Sampson's little way of telling you which way it's moving. And it has 100 joules of kinetic energy. I'm not going to make you calculate that. I'm just going to go ahead and tell you, okay? It's got 100 joules of kinetic energy. Now, this person, we see their hand here, they're applying an upward force as the thing moves downwards. And it's going to move downward 0.5 meters. So it's like imagine yourself catching a ball. The ball is moving down, but you're applying an upward force even though as your hand moves downwards. All right. So I want to know what is the ending kinetic energy of the box. So in this case, I have two forces acting on the box, right? So I have two different forces doing work on the box. I have gravitation, which is 60 newtons moving in the same direction that it's going. So gravity is doing positive work on the box because the force of gravity is directed in the same direction as the object's motion. So it's going to do 60 newtons times zero point 0.5. It's going to do 30 newtons. I'm sorry, 30 joules of positive work. The person's hand on the other hand, I guess I just said that, they're applying 100 newtons of upward force. That's in the opposite direction. It's going to do negative work. So 100 newtons times half a meter is 50 joules, but this 50 joules is going to be 50 joules of negative work. So in that case, if I add up the total work done on it, I have gravity does positive 30, the person's hand does negative 50. So the net work done on it is 20 joules of negative work. In other words, this object's kinetic energy that was initially 100 joules has now had 20 joules removed from it, subtracted from it. So I start off with 100 joules. Oh, I move my face in the way. How do I move myself out of this so you can see what I got here? And I end up with 100 joules with I have 80 less than I have. I have 80 now because I have 20 less than what I had before. Oh, and that was the last one. Okay. All right. Thanks for watching, guys.